Here, I would like to discuss with you a few basic equations that you really need to know, and you need really remember this one because it is very important for you to solve problems. Okay, the first one is about the rotational speed. Okay, here, please bear in mind that we have two types of speed actually. Okay, one is called linear and one is called rotational. So I think you are familiar with this, but sometimes students get stuck in this in converting these two type of speed. So linear means we are measuring the changes of displacement in terms of time. You know, speed is meter over time, so means there are changes of distance over time. So for linear here, so it is about when we are evaluating one point, go to another point, whether it is straight line or it is a zigzag line here, but it is clearly could be differentiate that point one is totally different location at point B. So that a quite easier, it's easy idea of linear speed. Okay, so but for rotational speed is we need to measuring about the displacement, but the difference is it's keep moving on the same track again and again. Okay, so that's why in unit, okay, for linear it is okay for us to use meter per second. Okay, however for the rotational speed here it is not not necessary, it is not suitable for us to use meter per second, because it quite confusing people when you are talking about a few meters after a few seconds in this rotating motion. So we, however, to express the rotating speed, so we are using the RPM or radian over second. Okay. So in centrifugal pumps problem, so we will use both velocity. Sometimes we will use linear velocity and sometimes we will use rotational velocity. So means that you need to know the relationship between these velocity. Okay, the common one that you need to understand is this one. So U is equal to R omega equal to pi dn over 60. So which is the U here is the linear velocity, which the unit is meter per second. So the R here is the radius, so in meter, and the omega is the angular velocity, which is in radian per second. Okay, so and then the D here is the diameter in meter, and please make sure that you really understand about the unit. If the question or the condition is given in rotation per minute, so mean you need to divide it by 60 here to make sure that you will get second. If the rotation or the rotation speed here, rotational speed is given per second, so please do not divide with 60, because we divide by 60 here to make sure that there is similarity on the units. You learn about similarity, dimensional analysis in fluid mechanics 1. That's why you need to alert it here, because the equation here is actually depends on the situation. Okay, I hope you remember the equation. At the same time, you know how to use that one. You understand, you really understand the unit for each parameter. So this is very important. Okay, the first equation is U is equal to R omega is equal to pi dn over 60. So normally the value of n here is given as RPM, rotation per minute or revolution per minute. So this is the first basic equation that you need to understand. So and then the second one. Sometimes in when we discuss about centrifugal pump, we are not discuss using the idea of head of pump. That's why if you buy a pump for your aquarium, normally people, the shop will ask you, so how much power do you want? So they are not asking you, okay, what is the monometric head or whatever head. okay, because there are no talking about head. So the relation between pump head of pump and power can be written like this one. Okay, so normally is power, it is equal to rho GQ and HP. So I think you already know this equation from fluid mechanics 1. Okay, so please remember that power is rho GQ times H. However, in this topic, we will have a lot of H. It is not just head of pump. We will have the manometric head. We will have an oiler head, and so on and so forth. There is a few type of pump head in this topic. So please make sure that you really understand the meaning of each head. So and then about the work. Okay, if we are talking about work, so work is torque times angular velocity. So it can be written as T times omega. So because the idea of work is force times the distance. Okay, so please remember this equation because all of these will be used to solve centrifugal pumps problem. Okay, we will go for this one. So we go first. We go for the head of pump. Yeah, I think you already heard about the idea of head of pump from fluid mechanics 1. So in this topic, in this chapter, we will call the head of pump here as the manometric head. So this is defined by British standard as the sum of the actual lift plus the friction losses in the pipe plus the discharge velocity head. So means that it can be written as this one. If you see this one, you will find that it is actually reflect your Bernoulli equation. Okay, so it is very simple. So however, for special pump, allowance must also be made for the velocity of flow toward the suction intake and any pressure differences at the water surface in the supply and receiving tanks. So commonly, the suction and delivery pipes are of equal diameter, in which manometric head can be written as this one. Okay, so what is the meaning of we have a equal diameter part here? So when we have equal diameter, okay, so means that we have a Q is equal to A times V. So if we have the velocity, okay, I'm sorry. So this is the continuity equation. So if the diameter is equal, so means that you have a same value of cross-sectional area. So if you have same cross-sectional area here, means that the velocity will remain constant. So means that if the suction and the delivery pipe have equal diameter, so means that the velocity for suction, the velocity here, and also the velocity at the delivery is remain the same. So if the velocity is remain the same, so means that the value of V2 minus V1 here will give you a zero value. So if we neglect this, if this value is zero, so means that we could write very basic equation for manometric head as P2 minus P1 over rho G. So why we always write P2 minus P1? Okay, please remember the idea, the mechanism of centrifugal pump. So we have volute. So we purposely have larger cross-sectional area in volute because we want to make sure that pressure at the outlet here is higher compared to the pressure at the inlet. So that's why in this calculation, okay, the higher the pressure at the outlet here will give you the higher value of manometric head. So if the manometric head value is bigger, is greater, so means that your pump capable to transfer water from lower level to the higher level. So the larger the value of manometric head, mean the higher the water can be transferred. Okay, this is the simple idea about the pump head or the manometric head. So if you have this system, Okay, for example, you have a pump here. So, and then, okay, you have you have one system like this one, because the system is circulate like this one, so means that we could say that there are no pump head, because if you see here, the inlet and the outlet head is actually remain the same. So this is the water level. So you have a water pump here. Inside the water pump, and this pump is send water for the same height. So actually, in this system, it is just for the education purpose. If you see this system, actually, without a pump, the water can be flow like this one. Means there is no flow. There is no purpose to have having pump like this one. Okay. Instead of purifying water and so on. For example, if you have a koi pond, for example, a fish pond like this. Okay, so for fish pond, you need to set up your pump like this one, because you have a debris here, a dirty water here, so you will suck using pump, and normally we will put a filter here to clean the water, and then we will flow back the clean water to this output. Okay. Okay, so and then for the second one, okay, you could see here if we have the inlet level here, and then this is the outlet level. So the pump location is here, but we only calculate the head of pump. The manometric pump is actually from the inlet level to the outlet level. So here, so we could say that the pump head is actually 2 feet. So, and then like this one, so we have a level here and we have a water level here. So this is the pump head. So in our syllabus, we will use SI unit. So everything will be shown in SI unit, whether it is meter, centimeter, or millimeter. So this is for your reference, how to take the manometric head. Okay, this is the another idea about the pump. Sometimes pump is located outside the source of water like this one. So for this one, okay, just bear in mind you need to measure the height from the inlet surface to the outlet surface here. So in this situation, we found that this is the distance between inlet and outlet surface, so means that this is the manometric head. Okay, but sometimes in textbook they will give you the idea of delivery head and also the suction head. So for the suction head here means that the distance from the input level here until the center point of the pump, and then the delivery head here is the vertical distance from the center line of the pump to the upper surface or the water surface for the outlet here. Okay, so and then this is more details sketch for this one. I think you could understand this one. Okay, let's say we have a pump here. So this is the center line of the pump. So and then this is the net suction head. Mean this is the water level. So and then this is the distance from the inlet water level to the suction to the center line of the pump. So and then this is the net discharge head, because this is the level where the outlet the level of the outlet. So and then we know that every time when water flow inside a pipe, so there is a losses. Okay, there are major losses, there are minor loss. Okay, so to make sure that our calculation is accurate enough to calculate the power of our pump and so on, so we must take into account all the friction element. So we could say that, so we have a friction in suction area. Okay, this is friction at the suction area, and this is the friction for the okay, this is the friction of the delivery area. Okay, now we have the delivery head velocity, we have friction head velocity, and we have the discharge. So here, if we want to explain this, we could say that, okay, this is actually the net head discharge here is a part of manometric head, because in this case, discharge of net discharge head and net suction head here, the total of these two is the manometric head or the head of pump. So, and then the delivery velocity head here is actually will refer to the V square over 2G. So this is the velocity head, V square over 2G. Okay, and then the friction here is referred to the losses. Okay, actually this is actually all about the Bernoulli equation that we learned in fluid mechanics 1. Okay, this is again another term about the head of pump. So I skip this one, and this is also, you could see from the video later on.